Everyone, good afternoon. I'm Christine Follett. I'm with AMI, and I'm here to facilitate a presentation today by our Director of Product Office, Zachary Bobroff, who's going to be doing a remote presentation. And this is on alternative methods to memory failure protection. So without further ado, I'll hand it over to Zach, who's going to give the presentation.
Hi, everybody. I'm Zach from AMI, as Christine just said, and we're going to be talking today about new methodologies to not only protect your system from memory failures, but predict them before they occur, and the best methodologies to go about doing this. So without any further ado, let's get started with the presentation.
Is it up? There we go.
So there we go. The first thing to talk about here is memory failures are not new. Why are we discussing them now? Basically, memory failures continue to be, if not the most costly cause of server downtime. And as every generation of DDR has happened, you've had DDR1, then DDR2, DDR3, DDR4, and now we're moving into DDR5. Every generation has more errors or is more error prone due to the clock speed going up, the shrinking of the die of the silicon, all things like this. So it's becoming a more and more pervasive problem that we need to address. We've built a lot of methodologies as an industry over the past 10 years of kind of detecting failing DIMM sticks and other things like this. But those methodologies are now reaching their limit of effectiveness. So how can we not only detect when a memory DIMM is failing, but can we predict when it's going to occur before it's happened? Because that's where the most value is going to be seen, is if you can predict a badly manufactured DIMM before it causes you a problem. So what are memory errors? There's a couple different types. Basically, you've got your DIMM faults, and within that, you've got soft faults and hard faults. Soft faults are one of those ones that you can't really do anything about, cosmic rays or particles. These are normally restorable when you have ECC type of memory. But then you've also got hard faults. This is where your memory will wear out. It's not meant to last forever. And they're manufacturing defects. Also, a DIMM may not be made perfectly. All DIMMs are not equal. These are repeatable errors that you want to recognize. So within the errors, again, now you've got two different types. You've got correctable errors and uncorrectable errors. These are normally seen only with ECC type of memory. Correctable errors, this is where you've got a single bit flip in a byte and you could fix that. Uncorrectable errors are where you're going to have a multi-bit flip. And when you have that multi-bit flip, you don't have that parity capability of restoring the original data. So this will typically result in an application or system crash. We're all familiar with the blue screen of death or a kernel panic. This is what can actually occur during an uncorrectable error. So when a DIMM is actually a DIMM failure or a failing DIMM, this is when it's acting outside of its expected behavior. Basically, it's not functioning like a proper stick of memory. And it will start with one failure. And when you combine that with environmental issues, wear, and implicit run context, this is going to be what causes that DIMM to actually fail. So data centers utilize system hardware. We'll go ahead and build this one out for running workloads for themselves and customers. So this is where we're making money off those servers. They're constantly running. They're not sitting idle. With the infrastructure in such high demand, you can't really have unexpected downtime for these. So you want to avoid unexpected downtime because that's where the money's going to stop flowing into one of these servers. And if ideally you would know when this is going to occur so that you can schedule that downtime and replace that memory, or even avoid using that memory during that period of when you know it's going to fail soon. So you've got 10 sticks of memory in there. Maybe you don't use one of them because you know this is a failing stick. Now, why is it with every generation of DDR, we're seeing greater failures? We already alluded to some of this, but with every generation, we increase the capacity. This is because we're able to fit more onto the stick with the shrink. The clock speed definitely increases. And with that shrink, there's more leakage coming from the silicon. So with the higher speed, capacity, and process shrink, the likelihood of errors increase. And in fact, with DDR5, we're already seeing as an industry that even two motherboards coming off the exact same production line will exhibit different behaviors with the same DIMM stick being inserted into both of them. So they're becoming very, they're not liking the environmental aspects of these electrical characteristics of different motherboards, for example. So if we go back to thinking about how traditional memory handling occurs, let's start there, and then we'll build upon this of how it can be improved. You can use an OS level driver, but many people today use an SMI handler. So an error occurs inside the CPU for the ECC error, whether that data is being accessed or there's a patrol scrubber going through and saw the error. It's going to then forward that to a BIOS SMI handler that's going to diagnose which DIMM did this error occur in, what rank it occurred in, and everything like this. And the BIOS then normally passes this information off to the BMC firmware on the platform that then logs it into the system event log or the cell. At this point, an administrator can come in through the out-of-band interface, review the system event log information. Maybe certain thresholds have been met for that DIMM. I've got 10 errors in the past hour, so then I know that this is a bad DIMM, or I suspect that it's a bad DIMM. So then they can go ahead and schedule it to be replaced, for example. But this is a very basic way of handling memory errors. The way that it was built on top of by a lot of the silicon vendors and the OEMs after that is they use something called leaky buckets. This is where I can set thresholds on a per hour, per day, and different capabilities on a per DIMM stick basis. And basically, if I have more than 5 errors in an hour, or if I have some sort of storm of these types of errors over a period of time that I set up, water spills outside the bucket. And then this is when I know that I need to do special handling of that DIMM. You could disable it, you could do different methods, but it's still very threshold based. So what I mean by that is that you're basically shutting off the problem after it's already occurred. So you're not taking advantage of knowing that problem was going to occur before it happened. You can also build very complex algorithms on top of this, and people have spent years developing different thresholds and different methodologies, but it's still very threshold based, where once the problem has occurred, you're already seeing it. So how do we predict this? If you could have your crystal ball and predict when a memory stick is going to go bad as opposed to it's actually failed, then you can take advantage of different system monitoring, or you can offload workloads from that DIMM before the failure occurs. You can schedule the maintenance, as we already talked about, before the system crashes. So you won't have a down system in your rack that you have to wait for somebody to come out to fix. You could schedule it so that it could be done the next day. It basically will allow you to properly utilize your data center admin's time. And even better, why can't I score each DIMM so that once the score drops below a certain threshold, I can have notifications occur so that I can plan everything else that we've talked about. So how are you going to build this prediction algorithm? It's pretty straightforward, and it's one of those things that it just is clear once you think about it, is that with enough data about a problem, you can predict future occurrences of that problem. So what's going on here is you have to see this in practice. You are basically logging every memory error that occurs in a data center. You then take that data compare it to the DIMMs that actually failed. So you're going to use older methodologies to predict or to detect when a DIMM has failed, then verify that DIMM has failed at the same time, and use all this data going through a weighted machine learning algorithm to predict those future failures. All you really do is look for patterns. If you see that the same types of errors keep occurring at regions A, B, and C, and then once you hit D, the entire DIMM is considered failed, you can build these heuristics into your methodologies so that once C occurs, you can already know that this is a bad DIMM and then plan for the future from there. So if we take a look at this updated methodology, you still follow the same type of path of where you've got correctable and uncorrectable errors going to the SMI handler. And at that point, you then not only send it to the BMC to be logged to the system event logger cell, you also pass it into the static memory model. So this doesn't need to be a model that is being updated in real time. You can compile this once every 6 months or 3 months based upon improved data that you're getting from servers across your fleet, and then push it through this model, come out with a memory score, and make this memory score not only available to the web UI so that somebody can come in and take a look at it, it can be available via Redfish or other RESTful APIs. And with Redfish, you can also use the host interface to expose this score to the operating system. So at all times, the operating system can make educated decisions on, should I stop using this memory for these workloads? Should I offload some things? Everything like that improves from there as well. So if we take a look at how this actually operates, you can see here it's kind of a accelerated failure just for demonstration purposes. But you can see here on the left, each error as it comes in, you can see the score slowly dropping. And then once it reaches a certain threshold, it's saying that, hey, this is a failed DIMM now. And you can see on that next error is an actual failure occurring. And on the right, you can see the pattern that it's matching. You can see where those errors were occurring inside the DIMM. And basically at a certain point, it saw a pattern that it knew from previous DIMMs. And then it would say, boom, this is a DIMM that is expected to fail, and it will move on from there. And this is not something that's cooked up in a vacuum. This has been done in real world examples. With our partner Intel that we worked with on this, it was deployed at Tencent and Meituan. These are both China CSPs for, I mean, the one on the right is actually for e-commerce, and the other one sells their services. But you can see they had a 5-time improvement in DIMM failure prediction and reduced downtime of systems. They simplified their workload migration policies to those areas that were not failed DIMMs. They optimized their page offlining policies. They reduced the unnecessary expenses in DIMM replacement and upgrading. So they were able to actually tell when these DIMMs were failing, because not only did this algorithm work on the front side, but it also fed back in on the back side where failed DIMMs were actually verified to be failed. On the right, you can see they were able to use this in similar ways to be able to prevent system crashes. They reduced them by 40% when it came to memory failures. What are some quick thoughts on ways this can be improved in the future? SMIs still eat into the CPU cycles of a system. You could use the BMC directly to, over interfaces like PECI, to pull the correctable errors directly, and you don't need to worry about involving an SMI. Handling of uncorrectable errors can result in catastrophic system crashes, so you still should capture those via an SMI handler, but we could look at new ways in the future to do this. But lastly, you really need to think about, how am I going to use this information in my infrastructure today to get the real benefits? Having this information alone doesn't mean anything if you're not going to use it in optimizing your infrastructure. So it's quick call to action. Memory failures continue to be a problem for the industry. Predicting DIMM failures have real world benefits, and you can see that based upon the real world results we just saw. Creating a model, it's not complicated. It only takes time and data. And working together as an industry, we can improve the overall compute performance by doing simple actions like predicting memory failures. And that's it.
Thank you, Zach. So we'll open it up for discussion. If anyone has any questions, comments, feel free to approach the microphone. Going once, going twice. All right, Zach, I think you're clear.
Thanks, everybody.
All right, thank you. Great job.